In exercise 13.28, we're going to follow that same procedure that we've been working towards practicing building up in the previous videos. So the first thing you will want to do here, just like the first thing we've done before, is to ask ourselves, do we need to form a new carbon-to-carbon bond? Now, the molecule on the left, the reagent, has sort of 1, 2, 3, 4 carbons with a methyl group coming off. And if you look at the molecule on the right, the product, you have the 1, 2, 3, 4 carbons with the methyl group coming off, but then at the end, you have a 5th carbon. And so in between that purple and blue carbon, you form a new carbon-to-carbon bond. Now, so far this semester, we've only talked about one way to form a new carbon-to-carbon bond. That's with Grignard reagents. We did learn another way to form them last semester. We'll cover that in B in this exercise. But for now, we can make this from a Grignard reagent. So how would we do that? Well, the first thing you would do is you'd take the new carbon chain that you want to add, and you'd take that, and you're going to make that your Grignard reagent. Where it attached to the other carbon chain, you will put magnesium bromide. So that makes this carbon here a nucleophile, and that's our Grignard. The Grignard is always going to react with an aldehyde or a ketone in this chapter, and so to get that, you would take your original molecule. Notice I'm putting a hydrogen at the end, right? Because here this has a carbon, but that carbon is coming from our Grignard, and so all the carbons we have in this molecule, all of these carbons are coming from the blue part here. No more, no less. Okay, so that's our aldehyde. And if we take that aldehyde and react it with this Grignard reaction, this Grignard reagent, remember that's a two-step process, and we explored this in a little detail in the previous video. Notice that we're doing retrosynthesis. We're starting with the product and we're working backwards. So if we use a Grignard reagent in our first step, and then remember in the second step you have to shake that up with some water to stabilize the negative charge that forms on the oxygen, we end up with this molecule, but it's an alcohol. Oops. So it's an alcohol. That's what we end up with after using that Grignard reagent. And we've discussed that and talked about how that happens in a little depth in previous videos in this chapter. Okay, well, that doesn't get us to our final product. This alcohol only has one bond to an electronegative element. The product has two, so we're going to have to do an oxidation. Now, there are two oxidizing agents that we can use. Two oxidizing agents we can use to do an oxidation. It's either going to be a weak oxidizing agent, so pyridinium chlorochromate in methylene chloride, no water present, or sodium dichromate in water and sulfuric acid. Either one of those. Now, technically, we need to choose between them. And we do that by looking at what type of an alcohol we have. Look at the carbon that has the OH on it. It's bonded to 2 other carbons. So this is a secondary alcohol. Now, for secondary alcohols, these two oxidizing agents do the same thing. So you could use either one of them. In practice, sodium dichromate would be a little less expensive, so that's probably what you do. This is probably what you do in a real laboratory in this scenario. But PCC would work, and I would give you full credit for that on the test here too. To turn a secondary alcohol into a ketone, you can use either of the oxidizing agents. So here, just because it's what you would use in a real laboratory, we'll use sodium dichromate. Oops. Actually, I'll just redraw this. So we'll have Na2Cr2O7 in water and sulfuric acid, so H2O, and H2SO4. And that would take the secondary alcohol to the ketone. So that's our Grignard part. That's the part of this exercise where we need to form a new carbon-to-carbon bond. So now we've done that. Now we have to think about how we can get this from our starting material using functional group interconversions. And that's this chart that we sort of built up in a previous video. So if we look at what we start with let me actually use a different color here. We start with an alkene, and we end up with an aldehyde. So we start with an alkene, and we end up with an aldehyde. And there are several ways that you can get from point A to point B there. You could turn the alkene into an alkyne, and then do a hydration. Or you could turn the alkene into an alcohol, and then do an oxidation. So either one of those would work. Two different answers that would be equally correct. Because it focuses more on the reactions we learned in this chapter, let's use this green method of making this transformation, of turning this alkene into that aldehyde. So the first thing we do, if you just looked at this and you didn't have that table or something, or if you wanted to rationalize the steps in that table, you would look at this and you'd say, okay, I don't have any oxygen here. I do have an oxygen in what I want. So how do I add that oxygen on there? Well, by asking that question, you answer it. You have to do an addition reaction. Okay, so we need to do an addition reaction to put an oxygen onto this molecule. Now, addition reactions use the extramolecular glue of pi bonds to stick new atoms onto the molecule. Here we're trying to stick an oxygen on. And for alkenes, you'll use that extramolecular glue to stick an oxygen on, and at first you just form one bond to the oxygen, and so you make an alcohol. Now we want the OH of the alcohol to go on this end carbon, because that's where it is in the molecule we want. We don't want it to go in the middle carbon. So, if you look at the original molecule, you have two carbons. The one on the end is only bonded to one other carbon, so it's primary. The one in the middle is bonded to two other carbons, so it is secondary. We want the OH to go on the less substituted carbon. That means the hydrogen goes on the more substituted carbon, and that is anti-Markovnikov. Anti-Markovnikov addition. And we only know one recipe for doing anti-Markovnikov addition. That's hydroboration oxidation. First step, add some 9-BBN. Second step, use hydrogen peroxide, H2O2, and sodium hydroxide, NaOH. And so that's how you get that first step in this green pathway. Notice you had 3 ways to add an H and an OH, but these first 2 are Markovnikov additions. This last one is the only anti-Markovnikov way to put an OH onto an alkene. Okay, so next, so we've done the addition reaction. Now, if we look at the molecule we want and compare it to the molecule we have, so this is what we want, this is what we have, you'll notice they both have the same number of carbons, they both have the same number of oxygens. The difference is in the number of bonds to the oxygen. Here there's only 1 bond to the oxygen, here there's 2. The number of bonds to an electronegative element increased. That type of reaction is an oxidation reaction. So we know we have to do an oxidation. And there are 2 types of oxidizing agents. The first one is the weak oxidizing agent, pyridinium chlorochromate in methylene chloride, CHCl2. That would turn primary alcohols into aldehydes and secondary alcohols into ketones. The second oxidizing agent, the strong one that you would want to know by heart, is sodium dichromate, Na2Cr2O7, in water and sulfuric acid, H2SO4. That turns primary alcohols into carboxylic acids. They both turn secondary alcohols into ketones, into ketones. So if you have a secondary alcohol, it doesn't matter which oxidizing reagent you use on tests in this class. But if you have a primary one, it makes a big difference. What type of alcohol do we have here? The carbon that has the OH on it is only bonded to one other carbon. So this is a primary alcohol. When you look at what becomes of the alcohol in your final product, you see a carbonyl, carbon double bonded to oxygen, with a hydrogen on one side. That is an aldehyde. So we want to go from a primary alcohol to an aldehyde. The oxidizing agent that does that is PCC. And so what we'd have to use here is PCC, pyridinium chlorochromate, in methylene chloride, CH2Cl2. And that connects all of the puzzle pieces so that to accomplish this transformation, what you would want to write out as the full correct answer is everything in this sort of green box here. First, you have to add an oxygen onto the molecule. You want to do it anti-Markovnikov. So you do hydroboration oxidation, and then you show what molecule you get after you add that one step. Then you want to oxidize that molecule so that you have a good electrophile for a Grignard reagent to attack. You only want to oxidize it to an aldehyde, so you use pyridinium chlorochromate in methylene chloride, and you'd want to show what the intermediate looks like after that step. Then you add your new carbon. So you have your Grignard reagent here. Remember to do that in 2 steps, one with the magnesium bromide, second, follow that up in a separate step with a water wash. That adds the carbon onto the chain and gives you the alcohol, so you draw the intermediate. Then you oxidize that secondary alcohol into your ketone using any oxidizing agent, really, but here, just for practice, we use the strong one, sodium dichromate in water and sulfuric acid. And we chose that specifically because in life, that's a little cheaper than PCC. And so that's the one you would really probably use. So you'd want to write all of that out for full credit on a question like this on the exam. Okay. Now B is an interesting one. If you follow the same sort of reasoning that we have normally, first ask yourself, do you form a new carbon-to-carbon bond? The answer very quickly is yes. Right? We have 2 carbons in the beginning. We have 1, 2, 3, 4, 5, 6, 7 carbons in the end. So we've formed many new carbon-to-carbon bonds. We've added a lot of carbons. And so far this semester, the only one that we've introduced this semester were Grignard reagents. Now technically we can create this molecule only using Grignard reagents. I mean, we can make all the new carbon-to-carbon bonds here only using Grignard reagents. It's just going to be a long journey. Now I'll show you how to do that. But after we do just the Grignard reagents, I'll show you how, if you remember the other carbon-to-carbon bond forming reaction from Organic Chemistry 1, it really simplifies your life in this exercise. Okay, first let's try to do it with the Grignard reagent, and this is going to be long. This is going to be difficult. So you can see how the more you know, the easier the solutions will be that you see. Okay, well, if we need to form a new carbon-to-carbon bond, let's pick these 2 carbons. We need to think about which carbons in the final product those could be. Now, we know that this carbon here is going to get attacked by a Grignard, right? That's the one that's electrophilic. It's slightly positive, and so a Grignard would be attracted to that. So we know that has to be one of the carbons in this original thing, because that's where we can form a new carbon-to-carbon bond. The other one could either be to the left or to the right, either way. And either way, you can go through this process of reasoning that we're about to and get a correct answer. I'm going to go with the carbon on the left, but you could just as easily go with the carbon on the right. So let's say those are the 2 carbons in our original molecule. And so we need to form 2 carbon-to-carbon bonds, because we have a carbon chain on the left here, and that means we have a new carbon-to-carbon bond here, and we have a separate carbon chain on the right. And there we have another new carbon-to-carbon bond that we need to form. So we're going to have to do at least 2 Grignard reactions in order to create this big long molecule. Okay, well we know that the Grignard reactions themselves will be these colored groups. Those are the carbon chains we need to add. So each of those are going to be Grignard reagents. So we could take those and just for our notes, making sort of sketches and brainstorming, we can take those and we know that where they were bonded to our original chain, we're going to have the magnesium bromide. That's what allows this carbon here to be nucleophilic and attack another carbon. So that's one Grignard reagent we're going to use. The other Grignard reagent we're going to use is this one here. So again, magnesium bromide. So those are the two Grignard reagents we're eventually going to have to use. Now, we have to give those Grignard reagents, which are nucleophiles, right? Remember, these carbons here are stealing all the electrons in these bonds, and they get a full lone pair, a full negative charge, and so they're really strong nucleophiles. We have to give those nucleophiles something to attack on our carbon chain. And if you'll remember, that what we usually give those to attack in this chapter are aldehydes or ketones. So what we really want to do is we want to take this alkyne and turn it in to an aldehyde or a ketone. So something like this. And actually, let me, just for consistency, take that same thing. We'll want to turn this in to an aldehyde, for example. We couldn't turn it into a ketone because that would involve adding another carbon. Right? So we can't add another carbon here. That would involve another Grignard reagent. So we just turn it into an aldehyde. So these are our two carbons. And actually, just so that, okay, we can do this. So those are our two carbons. So this is a functional group interconversion, right? Going from an alkyne to an aldehyde. That's like what we usually use to do a functional group conversion. That's where we would go to this table in our minds. So we're going from an alkyne to an aldehyde. And there's a way to do this. You would do either acid-catalyzed hydration or hydroboration oxidation. Now technically, those are different, right? Because this is Markovnikov, this is anti-Markovnikov addition. But here, the molecule is completely symmetrical. No matter where we put the oxygen, it's really on the same place, right? Imagine if you just take this and swirl it around. Now it's as if we put it on the other carbon, right? So both of the carbons here are equivalent because there's symmetry, and so it doesn't matter whether we do Markovnikov or anti-Markovnikov. It doesn't matter where the oxygen goes. Both of the carbons here are the same in terms of symmetry. So we can do either. Just because we haven't done it very much for practice, let's do acid-catalyzed hydration with this alkyne. Remember, to do that you need water, sulfuric acid, and mercuric sulfate, HgSO4, and this is acting as a catalyst. Okay, so now we have an aldehyde. Now we can combine this with one of our Grignard reagents. Well, here I've drawn this so that our aldehyde, our carbonyl, is on the right. And we would want that connected to this brown thing here. So we can get this brown thing, this Grignard reagent here. We can remember these Grignards are two steps. First step is the magnesium bromide, the Grignard reagent itself. The second step is a water wash to stabilize the charge on the oxygen that forms. So what you end up with at this point would be your new carbon-to-carbon bond. And actually, well, maybe it's good that we're doing this. We're going to have to do an extra step at the end for this, and I'll point out how this could be a little easier at the end. But here we go. Okay, so we're doing this. We've got this here. You can connect this brown group. That ultimately forms. And remember, after these, you break the pi bond. At first you have a negative charge there, you do the proton transfer from water, and you get the alcohol. So that's what we're left with at this point. Now, in order to add the other Grignard reagent, we need an aldehyde on this carbon. To get an aldehyde on that carbon, we have to eliminate this OH. So we're going to have to do an elimination reaction, and we want to form the pi bond to the left, right? If you do an elimination reaction on this, you could theoretically form a pi bond in two directions. The carbon that has the OH on it is the alpha carbon, and everything bonded to the alpha carbon is the beta carbon. Notice we have two. We have one to the right, we have one to the left. So you could do an elimination, get rid of the OH, and form a pi bond to the right. You could also do an elimination, get rid of the OH, and form a pi bond to the left. So either of those are possible. Notice that this alkene on the right is di-substituted, right? If you look at the two carbons in the pi bond, coming off of them is just 1, 2 carbon chains. So it's di-substituted. If you look at the one on the left, the two carbons in the pi bond, only one carbon chain is coming off of them, so that is mono-substituted. We want the one on the left, because that's where we need the aldehyde to be in order for this Grignard reagent to attack it. So we want the less substituted product, that's the Hofmann product. Right? Remember, the less substituted product is the Hofmann, the more substituted product is the Zaitsev. To get the Hofmann product as your major product, you use a bulky base. And so here we would need to do an E2 reaction. So the first step is to use tosyl chloride and pyridine. That replaces the OH with an OTS. So at first, you would have, you turn the bad OH leaving group into a good leaving group. And then you'd use a bulky base. And the bulky base you'd want to know is potassium tert butoxide, TBUOK, and that would give you the Hofmann product as your major product. Right? We don't want this Zaitsev product here. Okay, well now we want an aldehyde on this carbon on the left. The first thing to do is to form one bond to an oxygen there. And after we have one bond to an oxygen, we can get a second one. So we need to do an addition reaction. We need to add an oxygen. We want to make sure that the oxygen goes on the carbon on the left. Now the carbon on the left is only bonded to one other carbon, so it is a primary carbon. Oops. The carbon on the right is bonded to two other carbons, so it is a secondary carbon. We want the OH to go to the less substituted carbon. That means the hydrogen will go to the more substituted carbon. That is Markovnikov addition. I'm sorry, that is anti-Markovnikov addition, forgive me. If the hydrogen goes to the more substituted carbon, that is anti-Markovnikov addition. We only have one way of doing anti-Markovnikov addition of an OH and H. That's hydroboration oxidation, so you'd use 9-BBN, followed in a second step by hydrogen peroxide and sodium hydroxide. Now notice, this is really long, and we're forced to do this really long process because we're using Grignard reagents. You'll see there's a much shorter way to do this if you remember a carbon-to-carbon bond-forming reaction from Organic Chemistry 1. So I want to illustrate to you in this long process how the more reactions you remember, the easier your life will be. Even if you don't, you can always reason through it and do something like this, but the more you remember, the easier your life will be. Okay, so this is where we're at so far. We need to turn this into an aldehyde, right? We want this to look like this, so that our other Grignard reagent can attack here. Notice that so what we're doing is we have one bond to an oxygen, one bond to an oxygen, that becomes two bonds, that's an oxidation. And so we have to think about whether we want to use the weak oxidizing agent, PCC, in methylene chloride, or the strong oxidizing agent, sodium dichromate, in water and sulfuric acid. To determine those, we have to see whether we have a primary or secondary alcohol. If we have a secondary alcohol, it doesn't matter which we use. If we have a primary alcohol, we have to think about how much we want to oxidize the alcohol. The carbon that has the OH on it is only bonded to one other carbon. So this is a primary alcohol. What we want that to become is an aldehyde. So that's a carbonyl with a hydrogen on one side. So this is not as oxidized as it could possibly be. It could be more oxidized as a carboxylic acid. To just go to the aldehyde and stop, you'd use PCC. You'd use pyridinium chlorochromate in methylene chloride. Remember, the CH2Cl2 is just a solvent, reminding you that water is not there. Now that you have that aldehyde, you can take your other Grignard reagent and react it with it. So if you do that, remember that's in 2 steps. The first step is using the Grignard reagent itself. The second step is a water wash to stabilize the negative charge that forms on that oxygen. And what we have at this point is the number of carbons that we were interested in. So at this point, we have formed the number of carbons that we needed. We've formed the 2 new carbon-to-carbon bonds. So that's what we have now. Now, it would have been easier for us if we had added this purple one first, because then the oxygen, the OH, would have been on this other carbon. Now we have to move it back, and it's a little tricky to do that. But you could do an elimination reaction, like we did before, and I'm just going to do this a little fast. And again, I'm showing you this really long way to encourage you to remember all of the reactions from Organic Chemistry 1. So if you did, say, an E1 reaction here, you could do either E1 or E2. The pi bond will form in both directions, so you'll lose a lot of your product in this way. And that's another reason why it would have been better if we had added this purple one first and then done the brown one second. But let's say you did this. You could use concentrated sulfuric acid to do an E1 reaction. Oops. You'll really get 2 products here, but one of your products will be this here. And again, you're going to miss a lot of product if you're going to lose a lot of your reagent if you do this next step, because there's no preference. There's no way to do a Markovnikov or anti-Markovnikov addition here. So if you add some sort of addition reaction, you could end up moving the OH over here. Another point that I'm making by drawing all this out is, even if your reaction is crazy, even if it's inefficient, and these 2 steps are really inefficient the way that in this synthesis, I will still give you credit if you can make the product. So you're being graded on your ability to connect things, not your efficiency in connecting them. That would be something that you would think about more carefully in, for example, in Organic Chemistry 3 or 4 class. And that's good, always good to think about here. But last step, we just need to get that double bond to the oxygen here. So here there are 2 bonds to the oxygen, here there's just 1. So that's an oxidation. Because this is a secondary alcohol, so the OH is on a carbon that's bonded to 2 other carbons. Because that's a secondary alcohol, it doesn't matter which oxidizing agent you use. All oxidizing agents will take secondary alcohols and turn them into ketones. So, for example, you could use sodium dichromate in water and sulfuric acid, and that would accomplish that. Now, this is a really long synthesis, right? This is a huge number of steps. We were able to reason our way through it and sort of rationalize everything here, but it's kind of crazy. So although that may work, there is a better way to do this, but it involves remembering the reactions from the previous chapters. And so you could see how important it is to remember the reactions from Organic Chemistry 1. Okay, let's take this same synthesis And I'll show you how you can do that same synthesis much more easily and much more quickly using Organic Chemistry 1 reactions. The carbon-to-carbon bond-forming reaction you learned in Organic Chemistry 1 involved using a terminal alkyne. So remember, a terminal alkyne is an alkyne that has at least one of the carbons in it bonded to a hydrogen. This hydrogen was acidic. So you could treat that with a strong base, and the base that's strong enough to do this, that's usually used for this, is called sodium amide. It looks like this. NaNH2 is the way it's written. That could steal this hydrogen, the electrons go back onto that carbon, and now, just like with a Grignard reagent, you have a carbon nucleophile. And you can use that to attack an alkyl halide. To form a new carbon-to-carbon bond. And so that short process is what we can use here to form these new carbon-to-carbon bonds. So for example, we could take this alkyne, treat it with sodium amide, that strong base. That will turn this into this carbon nucleophile. Then we can choose one of our carbon chains and just turn it into an alkyl halide. So add a bromine or a chlorine on it. And when you do that, the carbon nucleophile can attack this bromine, or it can attack that carbon, kick the bromine off, do a standard SN2 reaction. So that what you'd form here is you have your triple bond, and you add the 1, 2, 3 carbons on it. Okay, so we could have that. Now I'm going to flip this over, just twist this around, just so that it sort of resembles what we're trying to get in a little bit more. Now we can get our aldehyde and use a Grignard reagent, just to attach this next one. So to turn this into an aldehyde, we want this to turn into, and notice the number of carbons here. We have 1, 2, 3, 4, 5. So I'm going to draw that. 1, 2, actually, 1, 2, 3, 4, 5. So these 3 on the end are there. These 2 came from the alkyne, and to get an aldehyde, we would need this here. And we can do that. That is one of the reactions that we learned in the functional group interconversion. You can turn this aldehyde, or you can turn an alkyne into an aldehyde by using either acid catalyzed hydration or hydroboration oxidation. Now the difference between those is whether you get Markovnikov or anti-Markovnikov addition of the oxygen. Here, we want the oxygen to go on the less substituted carbon, this carbon number 5 here. So this carbon is only bonded to one other carbon. Oops. So that is primary. This other carbon is bonded to 2 carbons. So that is secondary. So primary and secondary. We want the oxygen to go on the less substituted carbon. The hydrogen would go on the more substituted carbon. That is anti-Markovnikov addition. And so the way you can do anti-Markovnikov addition is with hydroboration oxidation, 9-ppn, followed by hydrogen peroxide, and sodium hydroxide. Now, if these reactions are really unfamiliar, if they're completely meaningless, they're random letters and numbers, I have the videos that walk through and explain the mechanisms for these from Organic Chemistry 1, and I encourage you, if you have the time, to walk through them so that these are more meaningful. Well, now that we have this aldehyde, we can just use our other Grignard reagent, right? We can use this carbon here, that carbon chain that we want to add. Where it connects, we have our magnesium bromide. That's one step. Second step is a water wash, so that we do a proton transfer to stabilize any charges. And the end result after that step is that the Grignard reagent attaches to what was the carbonyl carbon. The pi bond breaks. At first you have a negative charge on that oxygen, but then you do a proton transfer from water and you have the alcohol. And you'll notice we're almost done. We can go straight to our product here just by doing an oxidation. Notice, we have one bond to an electronegative element, here we have two. So the number of bonds to an electronegative element increase, that's oxidation. So we could either use PCC or sodium dichromate. The carbon that has the OH on it is bonded to two other carbons, so it's secondary. And with secondary carbons, it doesn't matter which oxidizing agent you use. They both oxidize secondary alcohols to ketones. So we'll use the cheaper one, sodium dichromate, in water and sulfuric acid. So notice how much shorter this synthesis is. But the reason why we were able to do this synthesis so quickly relative to the other way, which was crazy, right? This long, like, road trip that we went on. The reason we were able to do that was because we remembered this reaction from Organic Chemistry 1. It's the only other carbon-to-carbon bond-forming reaction you may have seen. And these carbon-to-carbon bond-forming reactions are really crucial. So if you see an alkyne, you can form a new carbon-to-carbon bond to that alkyne by using sodium amide and an alkyl halide. Okay, so that was a long one. I wanted to do that just to sort of illustrate the point. C is going to be a little bit shorter. The process of thinking is the same. First, you want to ask yourself, does the number of carbons change? Do you form a new carbon-to-carbon bond? On the left, we've got these 3 carbons with a methyl group. On the right, you have those same 3 carbons with a methyl group, but in addition to that, you have these 2 carbons on the right. So you do form a new carbon-to-carbon bond. And so, we're probably going to use a Grignard reagent, right? And in general, you'll use a Grignard reagent unless you have an alkyne. If you have an alkyne, your life will probably be easier if you use sodium amide and an alkyl halide. Now here we don't have a triple bond, so the Grignard reagent is what we're going to do. So the carbon chain that we add, that's what we're going to use to make our Grignard reagent. Where it bonded to the other chain, we add our magnesium bromide. And the other chain that was left, that's the alkyl halide that we want to start with. Notice where it was bonded, we just have a hydrogen there, because we don't want to add any carbons there. We're going to add carbons with our Grignard. So first step, Grignard. Second step, water wash. What we get is the molecule we want, but it's an alcohol. And notice, the more you do these problems, the more patterns you start to see. And so if you've been following along with all these videos, you would see that you'll start to see this pattern. You do the Grignard after a water wash, and you always get an alcohol, and then you always do an oxidation. Because here we have 1 bond to an oxygen, here we have 2. The number of bonds to an electronegative element increase. That's an oxidation reaction. Do we use PCC or sodium dichromate? Look at the carbon that has the OH on it. It's bonded to 2 other carbons. So this is a secondary alcohol. And you can oxidize a secondary alcohol using any oxidizing agent. It doesn't matter. It's only with primary alcohols that you have to be careful. So here you'd use the cheaper one, something like sodium dichromate, in water and sulfuric acid. Okay. And notice, that's the whole synthesis, because this molecule here is the one that they wanted us to start with. So I could just start with that there and move these reagents over. So this, everything written in this green area would be what you would want to write as the solution on a test question. So all the reagents and how each of those reagents change the molecule. Okay, So this is A, B, and C for this exercise. I'm going to stop this video here just so the video doesn't become unduly long. I'll do D, E, and F for this exercise in another separate